Welcome to my talk. I will talk about the things we accomplished this year for Scylla 3.0 and the things we are planning to do for the next year. I'm Avi. I'm the CTO of ScyllaDB and a co-founder. I have a lot of background in distributed storage and in virtualization, and now a lot more in databases. So let's see what we're going to talk about. So first of all, ScyllaDB is a database, so storage is a huge component. We're going to talk about how we're improving the ways that we utilize storage and different types of storage. We're going to talk about something that we're investing a lot in, multi-user and multi-workload. So far, you almost always see big data projects focusing on a single workload, a single type of query running all the time. But we are growing past that and allowing multiple workloads to coexist on the same cluster without interfering with each other. Attached to that is analytics. So ScyllaDB is not going to become a full-fledged analytics replacement. It's not going to replace your Spark cluster, but we are going to improve our integration with analytics engines. So your connection with Spark, with Presto, is going to become more efficient. And with the multi-user, multi-workload, you can do that in parallel with running your online workload. We're going to discuss the features and performance enhancements that we did in the past year and are planning, and look at the observability, which allows you to see what the database is doing, what you are doing, how you manage the database, and the ability to add nodes, remove nodes, repair, all of that. And last, we're going to take a little peek underneath and see how the infrastructure behind the infrastructure, so the database is the infrastructure for your application, but it also relies on infrastructures that we are building, so we're going to look at that as well. So first, storage, and if you ever invite me to your data center, then I expect it to look exactly like this. So the first major item that we are bringing with Scylla 3.0 is MC format SSTables. That's the technical name. It really is a file format that came with Cassandra 3 and Cassandra 4. So the first benefit that those new SSTable format brings is a reduced storage requirement. And that's done by merging repeating elements. So things like the column names that in the old format used to be repeated for each column are now compressed. And if you have rows that have some traits in common, for example, all of the columns have the same timestamp, then they can share that information instead of repeating it. Integer values are compressed. So depending on your exact layout, you can expect perhaps sometimes a small improvement, and sometimes it can be a very large improvement in the tens of %. So you can make more of the storage you have, store more data on your database. Large partition will be improved, large partition support. So this comes from having an index that can be searched with a binary search instead of the old format SSTables that had to be searched linearly. With the new format, you can do a binary search. And of course, when you have a very large partition, that reduces the amount of data you need to read from the index extensively, and also makes it much faster. This will bring us to be on par with Cassandra 3 and Cassandra 4, which use the same format, and that improves interoperability. You can bring in your SSTables from a Cassandra 3 deployment instead of having to go through SSTable loader, and that makes migrating a lot easier. And there will be a talk about that by our developer Vladimir, who will describe the process that went to bring this feature and the benefits. So another feature we're bringing is in-memory. It is a little bit running counter to the spirit of Scylla. Usually we're trying to increase the ratio between memory and storage. The more storage you have per gigabyte of memory means that you can reduce node sprawl, you can use larger and larger nodes, and reduce your node count. But with in-memory, it goes into the other direction. So you basically have a 1-to-1 ratio compared to the 30-to-1 or even 100-to-1 that you might have with the regular Scylla. And that means that your storage is going to be, your nodes are going to be more expensive. They will need more RAM. But the gain that you gain from that is having much lower latency, and you can have even more consistent latency than you usually get from Scylla. So if you have a really demanding workload where you need latencies that are much lower than usual, then you can go for in-memory. And there will be a talk by Gleb that describes how you can reach those really low latency thresholds. Another thing we're working on is incremental compaction. So with the traditional size tier compaction, you have this limitation where you have to keep 50% of your disk space free at all times. And the reason for that is that if you're compacting your data and you're compacting at your highest tier, then while your data is being compacted, a new SSTable that contains the same data is being generated. So you have the data present in two places at once. So you need this 50% of temporary space. And what we're going to do is make it incremental. So instead of having two huge SSTables that we will compact, we will divide them into small chunks or fragments. And as we write the new data, we will delete the old data incrementally so that at any point in time, roughly the same amount of data remains. And by the way, if you're worried that those fragments look a little bit crooked on the slides, I checked, it's only on the slides. On disks, they will be perfectly aligned to 4K. Yeah. Another thing that we're working on, this is a little bit more in the future, is columnar storage. So certain types of workload, time series workloads, can experience a relatively larger bloat even with a new format SSTables compared to specialized time series databases. So the way to handle that is to separate each series into its own files. And this way, you can do compression of that particular time series, which will be more efficient. And also, when you read a particular series, and usually in time series, there's plenty of series, but you're only reading just a few at a time. So you can read just those files, and instead of throwing away the data you don't need with row-based storage, all of the data in that file will be applicable to you. And it will increase analytics performance, which usually deals with the time series. Tiered storage is another way to get more value out of your database. There are now lots of different storage technologies available. And by mixing and matching them, you can mix your fast and more expensive storage with slow and cheaper storage. And this way, you can get a better cost performance. So different combinations can be your really fast NVMe with a slower SATA SSD, or perhaps if you're on a cloud, you can mix a network-attached storage, which is slower but relatively cheap, with direct-attached storage, which is more expensive but much faster and has much lower latency. There's also the possibility to mix SSD and traditional rotating storage, although with the prices of SSD going so low, maybe that's not really viable. And lastly, there's a new technology, non-volatile DIMMs called Optane by Intel, but also available from other vendors. And you can mix NVDIMMs and NVMe to get a really, really fast tiers that's almost operating at memory speed with the NVMe, which is also plenty fast. And this way you can get really good performance. The way you do this is you can do this in you can utilize this in different ways. First is you can take the low compaction tiers and place them on the fast storage, and the high compaction tiers, which usually have a lot more data but are compacted less often, you can place them on the slower tiers, and that is a simple way to get some of the benefit. And the other way is to actually move the data around. So if you see a particular row of data being accessed very often, you can move it from the slow storage to the high storage and vice versa, and this way you get faster read performance. All right, the next topic is multi-user and multi-workload. So whenever you have a shared resource, like the radio in this example, you have contention on it. And because this is a database conference, I'll talk about databases, not the radios. So the first thing is to notice is that we already have a lot of these contention problems in Scylla. When you have the database, different components of the database trying to utilize the machine's resources. So you have compaction trying to utilize I/O, and you have your queries trying to utilize the I/Os that come from the same disk. So you have contention on that. You have contention on the CPU. You have contention on networking. So we built a bunch of schedulers in order to arbitrate access to those resources. And the first application of those schedulers was within the database's internal components. So what we're doing now is pushing the use of those components one level up. And instead of arbitrating between different components within the databases, we're arbitrating between different users of the same data, and in the case of multi-tenancy, between users of different data, of different databases. So let's talk about managing the write rate. So there is a kind of tension between synchronous and asynchronous updates. When you're writing your data, of course, the data has to be replicated, usually 3 times, sometimes more. And the obvious approach to do it would be to go synchronous. So you accept a request from the user, from the client. You replicate it 3 times. You wait for all of the nodes to acknowledge that they have written, and then you send a response. And the advantage of that is that, first of all, it's really simple. And second, it means that the number of requests that are being processed by the system is bounded. If the client has 10,000 threads, then there will not be more than 10,000 requests in the system at any time, perhaps multiplied by a factor of 3 if you want to look at the individual replicas. But the downside of that is that availability is impacted, because if you're going to wait for a replica to respond and that replica just died, then it's not going to respond, and the client will not receive an acknowledgement, and the application will grind to a halt. So that is why you have tunable consistency levels. You can request a quorum write or even a consistency level of 1. And that means that the database has to, after the database acknowledges your write, it has to process the rest of the stuff asynchronously. And the problem with that is that the number of requests that the database has to process is no longer related to the number of client requests. The client might issue 10,000 requests concurrently, but each of these requests generates an additional asynchronous update that needs to be processed in the background. And those queues can start growing, and they start consuming memory, and things are, and of course, if they grow without bounds, then you will run out of memory, and again, everything will grind to a halt. So we have an elaborate scheme in order to manage the write rate. So on one hand, we don't want to be synchronous, but on the other hand, we do want to reduce the write rate so that we can retire those asynchronous requests at the same rate as we have incoming requests. And there is an excellent demonstration and some theoretical investigation by Nadav about how to achieve that. We have a controller that measures the number of background tasks that need to be processed and uses that to apply back pressure to the client in order to slow it down. So we are still operating in asynchronous mode so that a node crash will not impact your availability, but we're also not allowing the client to send a request without bound. We will throttle it in order to be able to maintain the cluster resources so that it can do the other work it needs to do. The other thing we are doing with the multi-user is workload isolation. So like I said, this builds on the work that we've already done. We expose the schedulers that we've written to control the internal processes of the database to the user. And the user can now dedicate, using CQL commands, you can dedicate some resources for particular workloads. So if you have an online workload that is running in parallel with an analytics workload, or perhaps an online workload running in parallel with an ingestion workload, you can say how many shares of the CPU you want to dedicate for each of them, and this way you can make sure that both of them continue to make progress at the rate you want them to go. And of course, there are multiple scenarios for that, and you can even have more than 2 workloads competing for the resources, and it's up to you to control. And while we do that, we will still provide the latencies that you expect and that you're used to, and there will be a very comprehensive talk by Glauber about this right after me or a little bit later. The next step after multi-user is multi-tenancy. So in multi-user, you have the same tables and the same key spaces shared between different workloads. So perhaps one workload is reading and writing, and the other workload is just doing analytics processing. With multi-tenancy, you extend that to completely separate tables from users that might not be even aware of each other. So you're able to consolidate multiple clusters that belong to different applications and run them on a single shared infrastructure. And this is similar to what you do with virtualization. You run different applications on the same server or with clouds. This is something that we've seen in many different ways. And it brings its own challenges with it. So first of all, you have to account for every single thing you do. Every CPU cycle that you spend on behalf of a user has to be accounted so that user cannot utilize more resources that they're entitled to. And you have to share the capacity. And usually that means that every queue in the system has to be split into separate queues, 1 queue per user. The reason for that is that you don't want a user that is issuing a lot of requests to stuff the queue with their request. And this way, when the database processes the head of the queue, it only has requests from that one user. It's very easy to end up in such a situation. So the approach we take for that is have a queue per user, and then the scheduler can pick which queue to process according to the resource allocation that the administrator specified in this case. So what issues are special to multi-tenancy? The first of them is small tables. If you're familiar with the architecture, Scylla splits the data among nodes and within a node among CPUs. But the metadata, the schema, the description of how the tables are laid out, that is replicated. So every node and every core has a replica of the metadata. And the problem with small tables is that as the cluster gets bigger, the amount of resource that you expend on this metadata starts to approach the size of the data on a particular node. So, and you might wonder, why is this special for multi-tenancy? You might have small tables in a non-multi-tenant cluster. And the answer is that as you have a bigger and bigger multi-tenant clusters, you have more tenants, even the larger tables become to seem small. So in comparison. So the way we address that is, instead of replicating the smaller tables across all the nodes and across all the cores within a node, we will do selective distribution. A really small table might reside only on 3 nodes and only on, say, 2 cores within those 3 nodes. And as it grows, we will allocate more cores and more nodes for that table. And this way, the small table problem will not impact us. Of course, that means that you have, now when the tenant grows, their tables become larger. You need to reallocate the space for them. So this is another thing that we need to address. And of course, security for a multi-tenant workload is much more concerning. It's not just like with a multi-user scenario where you don't want the users to interfere with each other. Here you might also have hostile users, and you don't want one tenant to be able to read or affect the other tenants in any way. So these are all challenges for us to implement multi-tenancy. And of course, it will be really great for us for Scylla Cloud. Analytics. So like I said, Scylla is not going to become a Spark replacement, but we are working to improve the way that Scylla interacts with analytics engines. So one way to do that is to improve full scan performance. Most of the analytics engines will do full scans on their tables and then perform their functions in memory. And the way to do that is to make queries stateful. There is a kind of tension, again, between stateful queries and stateless queries. Because we want fault tolerance, you want to keep as little state as possible on a node, because that node can disappear at any time. So if you're running an hour-long query and the node disappears midway through that, the whole query fails, and you don't want that. But on the other hand, you do want stateful queries, because those full scans are kind of streams. And if for every megabyte of data that you fetch, if you have to recreate all of the state needed to read that, then you're wasting a lot of effort reading and then rereading. So the way we address that is we introduce caches for those state. And as the query progresses, it first tries to look up the state in the cache. And if it finds it in the cache, then great. It continues as if it was completely stateful. And if it doesn't, then that means that a node crashed and either was restarted or we resumed the query on a different node. And now we can recreate the state from states that the client sent us and continue the query. We are also doing driver enhancement in order to reduce the number of hops. So we try to continue the query using the same coordinator in order to reduce those extra internal hops. And there will be a detailed talk about that from Boton. Another feature that we are adding to support, we've already added actually, to support analytics is allow filtering. That is a SQL feature that allows you to do server-side filtering for full table scans. So it reduces the amount of data that is sent over the wire and that the client has to process. We're also going to improve the driver in other ways. So you probably are familiar with a token-aware driver that can send a request to a node that owns one of the replicas for that request. We're going to apply that to full table scans as well. And of course, in that case, there is no single node that owns the data for the query. The data is spread all over the cluster, but the driver will know which is the next node that needs to process the data, and so it will again save an internal hop. Features and performance. So the major features that's missing from ScyllaDB compared to Cassandra is lightweight transactions, and we are implementing that now. Unlike Cassandra, which uses Paxos, we're using the more modern Raft algorithm. And we're going to make heavy use of that infrastructure. So not only to implement lightweight transactions, but also we'll use that for schema management. There's still problems if you have two nodes creating the same table, talking to two different nodes. So that problem will be eliminated. And also for cluster management. So things like adding a node, removing a node will utilize this infrastructure, and it will become more robust. And materialist views, which are one of the most, it's not one of the, it's the most complicated features that we have in Scylla, they will become much simplified once they start to use those lightweight transaction, the Raft infrastructure. And there will be a talk by Duarte about this feature and about the underlying implementation. So materialized views and secondary indexes, they're finally here in 3.0. So materialized views are one of the most complex features. So you have, apart from the coordinator and replica that you usually have in Scylla, you now have multiple view replicas that participate. And we had to choose between doing those updates synchronously or asynchronously. The problem with a synchronous update, that although it's much simpler, it also can result in an availability problem where you have one node failure causing even quorum queries not to go through, because a single update can involve the entire cluster if you have enough views. So we decided to go with the asynchronous model. And of course, that brings up the problem of generating back pressure, and Piotr will discuss it in his talk about how we handle all of those details. Another thing we're working on is improving streaming and repair performance, those background operations that happen as part of cluster administration. So first of all, we've improved the CPU and storage and network requirements. You will see less CPU used by streaming and by repair, and everything will become faster. But even more important for that, we've increased isolation. So we're now bypassing the cache and the mem tables during streaming and repair. And this way, if you have a workload that relies on the cache for your high cache hit rates, it will not be affected. And similarly with mem tables, so you will see less compaction as a result of streaming. And we also improved the integration with a scheduler so that problems with repair impacting latency and throughput will be much reduced after this. So this is also new in Scylla 3.0, at least part of it, and some will come in Scylla 3.1. And ACH will give a talk about that feature. Other things that we are doing is improving large partition support, so a lot of incremental work. SSTable index reads used to go all at once, so if you had a very large partition, we would need to read a large amount of data into memory, and it could be that the partition was so large that even its index was too large to read in memory. So we've gotten rid of that, and now we only read those incrementally and only consume a constant amount of memory at any time. When we evict from the cache, we used to have a problem that we could only evict a partition at once, and if the partition was really large, that would end up in a stall, and the system would stop processing requests while it got rid of that large partition. And the same thing with a mem table. When we move a partition from mem table to cache, that used to happen all at once, and so it could stall the machine. But now this happens incrementally, row by row, and so even if you have partitions that are larger than memory, you will not see any effect on latency. We are also introducing a shard-aware drivers. We already have those for Java and Go, but we will gradually introduce them for other languages. So in the same way that the token-aware driver is able to access the node that is responsible for a bit of data, it will now be able to access the core that is responsible for a bit of data, so that it removes an internal hop. It prevents overloaded cores. So if you have too small a number of connections, Globber will always tell you add more connections, add more connections. Now you no longer need to do that because it will have exactly one connection per core, and the load will be distributed evenly. And this is one of those features that improves everything. So you get better throughput, you get better latency, and it's all completely compatible. You can still use the standard drivers, or you can use ours, and our drivers will work with Cassandra, so there's no compatibility problem. And there will be a talk about by Piotr about that. It's a different Piotr from the other talk, but yeah. Another important topic is observability. It allows you to see what's going on in the database, especially if there are problems, but even if not, it's good to understand what's going on. So we've invested a lot of work in improving observability. One thing is the new monitoring stack. So we have improved dashboards with more data, and they're more flexible. You can switch to shard views, you can switch to cluster-wide views, and more pertinent data. We've moved to Prometheus 2.x. This gives you a smaller footprint for your data, so it is more efficient in storing your metrics data. And we simplified the deployment, and Amnon will describe this in his talk. The dashboards and the SQL tracing facility allow you to do a performance drill down. So if you have a problem, you can use the dashboards and tracing to try to isolate exactly where the problem is and find it and fix it. And there was a talk that was supposed to be delivered by Vlad, but unfortunately he broke his leg, so I'll have to do that instead. The Scylla dashboards allow you to improve your applications. So we added a lot of what we call badness metrics. So a badness metric is usually 0, but whenever something bad is happening, the counter climbs. So a typical example is not using prepared statements. So as long as all the statements are prepared, then the counter will remain at 0. But if you have some part in your application that's not using prepared statement, that metric will jump, and you will immediately see where the problem is. And Shlomi will give some examples of that in his talk. Manageability is very important. So of course, you need to be able to administer the cluster, and we put a lot of effort in making things as streamlined as possible. And some of the things for that is role-based access control. So this is really a baseline, because a lot of other manageability features are built on that. So things like security, of course, and audit use roles to drive them. And also workload isolation, which I described earlier, can use the roles in order to define exactly what kind of service level a particular user or tenant should expect. And we're also improving the integration with other directories. So right now, we only support internally defined users and access control, but we're now adding integration with LDAP so that you can integrate with your enterprise directory. And Jesse will talk about that. The traditional Scylla and Cassandra management is node by node. You have node tool, which manages a node. Because that is not what you want to do, you're managing a cluster, we have Scylla Manager, and Michal will describe the features and the benefits that the Scylla Manager brings you in his talk. Lastly, Kubernetes, like Dor said, it's becoming ever more popular, and integration, and we are adding integration with Kubernetes. Unfortunately, Kubernetes, because it is yet another virtualization layer, adds its own performance problems. So Moreno will describe what those problems are and how we can eliminate them, and the benefits that you can expect by applying those techniques. And lastly, the most manageable thing that there is something that you don't need to manage, and that's Scylla Cloud. So it's a complete offload of the management effort. It can be a lot cheaper. So if you're running a relatively small deployment, then instead of having someone to manage a small deployment, you can offload that to Scylla. Because it's running on a very efficient infrastructure, then we can offer much better cost, and also, like Dor explained in his talk, even when the workload is not ideal, it's not perfectly balanced, Scylla will tolerate that better than the competition. And last, the infrastructure. So building this database engine required us to invest a lot in infrastructure. And that infrastructure is called Seastar, and below that we utilize Linux and XFS. So we've sponsored some work for Linux to improve XFS, which is the underlying file system that we use. We identified several bottlenecks, and by the way, 2 different cloud vendors told us that Scylla is one of the most I/O-intensive applications that they're running on their I/O-intensive instance types. So we tend to discover those issues ahead of everyone else, and we also have to fix them. So we contracted some work in order to improve XFS, and also to add new APIs to the Linux kernel that allow you to perform those I/O-intensive operations more efficiently. And perhaps other applications will also benefit from that, completely unrelated to Seastar and Scylla. We've done a lot of work on Seastar itself. So we've improved the CPU scheduler. We have a new I/O scheduler that is better tuned to how the disk works. So it measures the read and the separate read and write bandwidths and the separate read and write IOPS, and it is able to adjust its behavior according to the exact workload that's running. We've added native streaming support, and that's used in repair and streaming, which reduces the number of packets that are sent to stream large amounts of data. And it's nice to see that other projects are starting to use Seastar, and the most important in my view is Ceph. Ceph is a distributed file system, and a distributed file system is very similar to a distributed database, except that instead of managing structured data like a database, it manages unstructured data, files. So it makes sense to build a distributed file system on top of Seastar, and Kefu of Red Hat, or maybe IBM now, will talk about how they're doing just that, and I see a great collaboration in the future with this. And that's it. I described a lot of talks by my colleagues at ScyllaDB, but really the most important talks are the one by your peers that show how all this technology gets applied in real life and how it hits real-life workloads, and not just the ones that we think it should do well, but also the ones that matter to you. So attend those talks and enjoy them. Thank you.